once, let's reach out and grab it.
Yeah.
Together we'll nab it.
We'll hitchhike bus or yellow cabin. Moving right along. Footloose and fancy free.
Getting there is half the fun. Come share it with me.
Moving right along.
We'll learn to share the load.
We don't need a map to keep the show on the road.
Hey, Fonzie, I want you to turn left if you come to a fork in the road.
Yes, sir. Turn left at the fork in the road. Permit.
I don't believe that. Moving right along, we found a life on the highway.
And your way is my way.
So trust my navigation.
Movie stars with flashing cars and lights with the top down.
We're storming the big hill.
Yeah, storm is right. Should it be snowing?
No, I don't think so.
Moving right along.
Footloose and fancy free.
You ready for the big time?
Is it ready for me?
Moving right along. Moving right along. Moving right along. Moving right along.
Maybe you better pull over.
Yes, sir.
Oh.
This is CS50, and this is the end of week 0, but the start of a beautiful friendship. We are so excited to be here at Yale University for the very first time with our friends Skaz and Jason and Andy, all 40 of CS50's TFs and CAs here at Yale, and all of you. And in fact, it's probably time to... Even though most of the lectures will indeed be in Cambridge this year, the reality is that by design and very much deliberately in CS50, I do think we're nearing the point, technologically and pedagogically, where it can be a superior educational experience to engage with some of the course's material online. Indeed, the reality, and I believe this philosophically, is that lectures are not a particularly effective means for delivering fairly complex information, certainly over hour-plus long spans of time. And indeed, every few minutes, I remember myself in college, you zone out for a moment, you miss some complex topic, and you're gone pretty much for the next 45 minutes. And the reality is that whether you're here in New Haven or Cambridge or beyond, the simplicity of having the ability to pause and fast forward, rewind, hyperlink to related resources, search full text transcripts and the like is an opportunity that I dare say for our online students well beyond New Haven offers them an opportunity to really grasp the conceptual material that we introduce in lectures all the better. But ultimately in CS50 is the student's experience is characterized so much more by the course's problem sets or weekly programming projects, the course's sections led by the teaching fellows, the nightly office hours led by the course assistants and the teaching fellows, and indeed such events as CS50 Puzzle Day, CS50's Hackathon, the CS50 Fair, weekly lunches, and so much more. And so whether you're here in New Haven or tuning in from afar today in Cambridge, and we'll see you again soon, the reality is this is one and the same class, and we are so excited to be here all together today. And so at the end of the semester, whether here or afar, will hopefully you wear proudly, happily, and perhaps with a bit of relief, the shirt that bears witness to you having taken CS50. So where did we leave off on Wednesday? We took a look at computational thinking, and that's to what we distilled computer science into, at least for now. But we distilled it further into at least 3 component elements. Inputs, so what is the problem we're trying to solve? Outputs, what is the answer we're hoping to get? And the representation thereof. And we won't dwell here on after on binary and even ASCII and the like so much, but rather take for granted that we can represent this information because the far more interesting parts of those problems are not just the inputs and outputs, but the algorithms that go into solving those problems. And you might recall from the other day that we took a fairly traditional concept of looking someone up in a fairly large phone book, or more generally, digitally these days, just a very large data set, a really big contacts list with lots of names alphabetically sorted, and we realized that while I could approach this problem simply by using a linear approach, page by page, or even 2s at a time, we realized that the more intuitive algorithm, just kind of dividing and conquering the problem, again, and again, having it with each time gave us this green result. And it's so much flatter because it suggests that even as this problem gets bigger and bigger, as is the case these days with data sets in reality, Facebook and Google search results and the like, does our algorithm perform just as effectively with those bigger bytes as it did even with the smaller bytes. Now, it begs the question, what can we actually solve similarly with this kind of intuition, this sort of division and conquering? Well, we could do something like this today here. We could take attendance, so maybe like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Not going to be all that efficient. So wait, grade school, 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. But could we do a little better? I'm pretty sure I can't do this by myself. So if you'll humor us for just a moment, we brought with us an algorithm that's just got 3 steps, but it does require, if you don't mind, that all of us stand up, if you would. So, with all of us now standing, step 1 of this algorithm is the following. Stand up and assign yourself the number 1. So at this point in time, literally everyone in this room, hopefully, is thinking to themselves, however awkwardly, the number 1. Now, step 2 of this algorithm is going to involve the following. Step 2, pair off with someone standing, add your numbers together, and adopt the sum as your new number. All right, quick sanity check. What number is everyone thinking of now? All right, so 2, except maybe for one awkward, lonesome person if we have an odd number of people in the room. All right, so one person might still be the number 1, that's fine. But step 3 here, one of you should sit down, the other should go back to step 2. And repeat if you would. So if still standing, you should be among those going back to step 2. Keep going. All right, few people still standing. So if still standing, pair off with someone. All right, whittling down. Few people still standing. I'll help if need be. Remember, the key takeaway here is how much faster this is than me counting. So let's see. I can help out. So what number are you still thinking of?
I got 44.
44. So you go ahead and sit down. What number are you thinking of?
74.
74. All right, go ahead and sit down. Who else is still standing? 86. And is anyone else still standing? What number? Okay, wait, I heard 67, and then in top? 32. Anyone else still standing and thinking of a number? Oh, hi, sorry. Be right back. 42. Anyone else? Okay.
47.
47. Is anyone else still standing who hasn't been counted? All right, so the final number of people in a room that has 497 seats is... all of which are filled It's 390. So, okay, so this is great. We will soon discuss the notion of a bug in a computer program, but we'll come back to that before long. But in theory, what might have happened just now? So even though there were 3 big steps to this algorithm, each of those was just kind of one big operation, and there was this cyclicity to it in that if you were still standing, you kept going from step 3 to 2, step 3 to 2, step 3 to 2, but what kept happening on each iteration, each cycle of this loop? What was happening elsewhere in the room? Not only the same thing, but what was happening to half of you? Sitting down. And so therein lies this insight, much like the phone book example, in that if half of you are sitting down each time, the problem is starting with maybe 400 people, then to 200 people, then 100 people, then 50 people, and so forth, until we whittle it down, in theory, to just one person thinking of the total value of everyone. Now, in reality, some social dynamics and some arithmetic errors might contribute to that ultimate bug, but in theory, while I was still counting away, taking several dozen steps or hundreds of steps to count yourselves, to count a room full of 500 or so people should have taken far fewer steps, because you can only divide 500 in half so many times. And so just like with the phone book example the other day, did we have something logarithmic, so to speak, whereby if we were all operating in unison and ignoring the addition errors, would we have achieved exactly that kind of running time? Now, to be fair, kind of cheated in that I leveraged another resource, right? Whereas it's just one of me, I leveraged hundreds of you, but that might be said to be an example of parallel processing, a state of art very much in vogue, where computers these days have multiple CPUs, or more technically, multiple cores, and can truly do multiple things at once, much like you all were doing there in parallel. But recall that what we also did on Wednesday was try to capture this intuition and formalize it in code, something like pseudocode. And in fact, and I hope you forgive, it's like 80 degrees in here, so I'm going to take this off for just a little bit. What I thought we'd do is transition now to an application whereby we again engage the audience, but write a program in English-like syntax with which to solve this problem here.
It's peanut butter jelly time. Peanut butter jelly time. Peanut butter jelly time. Where you at? Where you at? Where you at? Where you at? There you go. There you go. There you go. There you go. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Do the peanut butter jelly. Peanut butter jelly. Peanut butter jelly with the baseball bat.
In that video, but it is a little addictive, if not a bit annoying. But to do this, I thought what we'd do is try to write a program together for which we need 3 volunteers. Have to be comfortable on camera and the internet. Sam, come on up. Okay, purple shirt right here. Come on up, and from over here, let me go a little farther back. Crimson and blue shirts. Come on up. Perfect. And come on up. Come on up. Come on up. All right. And what's your name? Erica. David, nice to meet you. If you'd like to take this seat here. This is Sam. And what's your name? Antonio. Antonio, nice to meet you. Erica and Sam, if you'd like to have a seat here. What we've come prepared with, as these guys are discovering, is the ingredients with which to make a peanut butter and jelly sandwich. Now, this might be something that you take very much for granted, but we've given each of our 3 volunteers here, or 2 volunteers and Sam here, a loaf of bread each, a plate, a knife, a jar of jelly or jam, and a jar of peanut butter. And the goal at hand now is going to be for these 3 to make a peanut butter and jelly sandwich. But what we're going to do is expect the audience, since all of you surely know how to do this so well in reality, are going to provide us with the step-by-step instructions, the pseudocode, if you will. So I'll play the role of scribe here, and I've got a little to-do list, and so as each of you one at a time calls out a potential instruction, I'll write it down, repeat it as needed, and then you guys are going to make a peanut butter and jelly sandwich only by doing what you are told. So think of yourselves as computers. You can only do what you're told. No assumptions, no questions. You just need to do it. So who would like to hazard the first instruction for making a PBJ sandwich on the balcony there?
Open the bag of bread.
Open the bag of bread, if you will. All right, so let's iterate and get a little more precise. Good way to begin, though. Step 2, someone else. Oh, now no one wants to volunteer. Step 2, in front.
Open the inner bag of bread as well.
Open the inner bag of bread as well. Great, we're learning. All right, a little more precise. Let's get this working. Yes, in green shirt.
Gently remove 2 slices.
Slices of bread. Gently remove 2 slices of bread. That's good. Step 4, someone else. Over here, yes.
Bread on plate.
Place bread on plate. Step 5. Step 5, yeah.
Lightly place hand on top of peanut butter.
On top of, oh, hand. Place hand on top of peanut butter. Is that what I heard?
Yeah, and unscrew.
And say it again.
Unscrew and put the lid next to the peanut butter.
And put the lid next to the peanut butter. Lightly place hand on top of peanut butter and unscrew and put the lid next to the peanut butter. Okay, step 6. Step 6. Someone else, yeah. And say it again. And repeat step 5 again. Which is going to create a bit of a problem now if we're doing this step by step. So now we go back to step 5. Lightly place hand on top of peanut butter and unscrew and put lid next to the peanut butter. Then grasp the peanut butter and repeat step 5 again. All right, so we'll override that infinite loop, if you will. Step 7, someone else. Yeah, and back.
Grasp lower half of the peanut butter jar with one hand and top of the other. Turn it opposing in direction.
Okay, wait. Okay, and on top of other. On the other hand, on the other top. Do you want to just come up here? Okay. Anyway, how do I finish the instruction? What's the rest of the instruction? Ignoring that part. Okay, so let's start over. Step 7. Grasp with opposing hands. This is good. This is actually good. And plastic jar. And twist. For 2 seconds. Okay, just open the peanut butter jar. Okay. I hope you'll forgive. Okay, so let's assume we got there. Open the peanut butter jar. Yeah, excellent. All right. All right, step 8. Let's go. Step 8. Yes, in back. Insert. Good. Step 9. Yes. If out of the peanut butter jar and what? And put knife back into peanut butter. Good job. Okay. Okay, step 10. Step 10. Put the knife out.
And then remove the seal.
And then remove the seal. Nice.
Off the peanut butter.
Off the peanut butter. All right, step 11. Yeah.
Gray computer follow blue or red?
Wait, say again?
Gray computer should follow blue or red.
Oh, gray computer. Okay, gray computer, follow blue or red computer. All right, good. All right. Bring us home. Couple more steps. What's next? Step 12. Step 12. Yeah.
Put one of the slices of bread, like gently,
One of your hands. And then step 13. Yeah.
Use knife to gently spread peanut butter onto slice of bread.
On slice of bread. Good. Pretty good. Step 14. 14, yeah.
Undo step 13.
Undo step 13. Let's move on to the jelly. Come here. This is a 100-step program. We're on step 15. Yeah.
Repeat step 7 through 13 using the jelly.
7 through 13 using the jelly, because those went so well. Okay. Repeat steps 7 through 13 using the jelly. So grasp the lower half of the jelly jar with one hand on top, the other hand of the other top. Ignoring that part, grasp with opposing hands the lid in the plastic jar at the bottom and twist for 2 seconds. Then open the jelly jar. And lastly, let's try to give us something edible. Step 16. Last step.
Call mom to help you make a
All right. So why don't we leave it there? Thank you so much to our 3 volunteers. If you'd like, we have a CS50 stress ball for you.
Oh,
It's going.
Do I get one too?
Yeah, it was going to be a sandwich, but okay. All right, so what was the point beyond having a bit of fun with the algorithms? But the reality is that even when you're programming a computer, do you need to be super precise, right? As complex or intimidating as your own computer might very well be to you, at least when something goes wrong, the reality is it's a pretty dumb device that was invented by us humans and can only do a subset of what we do, sometimes certainly faster, but it doesn't know how to make assumptions. It doesn't know how to be on the same wavelength as you. It will only do precisely what you tell it. And you'll be struck, perhaps, as we start writing actual code with the first problem sets and beyond, just how easy it is to make an assumption as a human and not anticipate, oh, I need to handle that case or that corner case, so to speak, that might very well arise if, for instance, Sam had the only squeezable jar of jelly, whereas everyone else had some glass jars as well. So before we turn our attention to some actual code, allow me to introduce the course's heads here at Yale, our friends Skaz and Andy and Jason, to come up and say hello.
Jason somewhere. We've lost Jason temporarily. Okay. Hi again, everyone. My name is Skaz. I've been teaching at Yale since 2001, and when I'm not teaching, my research is in robotics and artificial intelligence. And the announcement that I have today is that starting in a couple of weeks, we're going to be bringing some supplementary material to CS50 to talk about intelligent software. We're going to talk about how places like Netflix and Hulu can recommend movies that you might want to watch. Or we'll talk about how driverless cars actually work. And we'll be able to ground these things in the concepts that you're learning in this class today. Because all of these things are built upon the same foundation. And that's what this series will explore. So I'm really looking forward to seeing more of you all, and you're going to get to see more from all of us very soon. Let me then introduce Jason.
Hi everyone, my name is Jason. I unfortunately went to Harvard as an undergrad. That's going to get cut out of the actual stream. And now I'm here as a lecturer in the computer science department, and I'm helping run the course with Skaz, David, and Andy.
All right, hi guys. So my name is Andy. I am actually the only Yale student on this stage right now. I'm in Berkeley College, originally from Solon, Ohio. There we go. And I was one of those kids where when I came to Yale, I really thought that I would never have to look at a number ever again. And then I realized that you needed both science and QR credits to graduate. And so my freshman spring, I took a class, intro CS class here at Yale. I was like, this is actually pretty cool. And while I actually ended up declaring as a global affairs major, the skills I learned in CS and programming are so applicable to any field you choose to do. And the staff here at Yale, we've been so hard at work to prepare for you guys, and we look forward to seeing you all in section and office hours. So yeah.
Thank you. So just before class began, we had an opportunity to walk around campus with a cell phone and take some selfies in video form of really my first tour of Yale's campus here. And so we thought we'd share a rough cut of exactly this as Skaz and Andy and Jason took me around campus.
Nice to see you. Can we go on a tour?
Let's go on a tour. Woo, tour! This line has been there for a while. Woo, CS50.
Hey, come on, hurry.
Go.
You should show that one up. Harkness Tower.
We saw that a couple times. Watch out for the bike! Hi, Frank.
What's up, guys? Hey, good to see you. Welcome to the video.
Don't act too excited. I love Silman.
It's been about 3 hours since Jason had ice cream and Nutella, so we've got to stop back at Silman for a little bit.
It's not even that I've had Nutella yet. It's just the fact that they have it here is so amazing. Dude, there's Nutella at every meal.
Last year too.
Yeah. I don't know much about Yale so far, but I do know that's TD over there, and that's considered off campus.
Here we have Gothic architecture, world famous. We have some more Gothic architecture, and construction, and more Gothic architecture. Hi, this is where we're having office hours Tuesdays through Thursdays in Hogwarts, essentially.
All right, that's it for the tour. We are at Yale University's Law School where today's lecture is about to take place. Let's head in.
And that brings us here now. So thus far, we've been focusing on pseudocode, which is this English-like syntax. It has no prescribed specification. It's just you use some intuitive language if you wanted to explain what you want to do. But let's begin now to transition to code, as most people would say, but more precisely, something known as source code. This is the language that humans write that computers ultimately, possibly after some number of steps, ultimately understand so as to know how to do something. Now, you saw a glimpse of this perhaps on Wednesday. This is an example that incredibly underwhelmingly, when run, simply says, hello world. And it's written in a language called C, which is syntactically very similar to a lot of other languages that you might not know but might have heard of, like Java and C++ and Python and Ruby and the like. And indeed, we'll spend much of the semester using C, and then toward the end of the semester building upon it and introducing any number of other languages, among them PHP and JavaScript, a database language called SQL. But with C, we have this bottom-up understanding of exactly how computers work, what you can do with them, and how you can solve problems all the more effectively by this layering that we discussed on Wednesday and standing on the shoulders of others. But more on that to come. Today, we look at a simpler environment, but a fundamentally identical environment known as Scratch by our friends at MIT's Media Lab. This is a graphical programming language, Scratch, whereby you can drag and drop things that look like puzzle pieces that only interlock if it makes logical or programmatic sense to do so. But it's going to allow us to have a conversation about all of the same programming fundamentals that some of you might know already, that many of you might not know anything of, without having to get bogged down, frankly, in the intellectually uninteresting syntax of semicolons and parentheses and quotes and the like, all of which early on are a distraction to what are the interesting and genuinely useful ideas. So let's take a quick glance at the environment here so that you know what awaits. And in fact, among the games we can play are a few programs written by CS50's own former students. One of them, myself, I'll be this one written in graduate school for me. If I could take one volunteer who's willing to play a game for the very first time. Sure, come on up. What's your name? Angela, come on up. So Scratch has been out for a few years, and when I was in graduate school, I was cross-registered at MIT, taking Professor Mitchell Resnick's course on educational technologies, and we were among the very first students in the world to actually beta test Scratch, and my project was what Angela has now graciously volunteered to play, called Oscar Time. So I'm going to go ahead and double-click the icon here. It's going to open up a programming environment that we'll soon dive into. I'm going to full screen it for Angela here. I'm going to hit the green flag in just a moment, and then a whole lot of trash is going to fall from the sky, and you're going to use the mouse here to actually drag and drop the trash into Oscar's trash can. So if you want to go ahead and click the green flag, the game will begin.
Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because
green these days, just be throwing everything in the trash. And so what one of CS50's own staff did, Jordan, whom you might meet today, has actually updated this for today's times. And so allow me to open up a remix instead for Angela, and we'll play this instead for a few moments, where now you're going to have to decide between whether to throw something in the trash or recycle it or compost it. So there's a bit of pressure on you to get this right in front of your 392 to 497 classmates here in the hall, if you would.
oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. If you really want to see something trashy, look at this. I have here a sneaker that's tattered and worn. It's all full of holes and the laces are torn. A gift from my mother the day I was born. I love it because it's trash. Oh, I love trash. Anything dirty or dingy or dusty. Anything ragged or rotten or rusty. Yes, I love trash. Here's some more rotten stuff. I have here some newspaper.
Are actually compostable. But thank you to our volunteer, Angela. We have a stress ball for you here as well. So thank you. So this one was written by me, but now one by an actual former student who implemented this, which is a game, all in this language called Scratch that we'll soon peel back the layers of. But if we'd like, how about another volunteer? Right, come on up. What's your name? Lance? Lance? Lance, come on up. Nice to meet you. Come on this way. So this one might have a theme familiar to some of you, but you'll see too that there can be interactivity whereby you can actually be the role of a character moving around. Nice to meet you, David. I give you Pikachu. Instructions are about to come on the screen, but in short, you're going to want to catch the tasty stuff and avoid the bombs and other things. With the cursors entirely. So hit the space bar. Pikachu. Catch the stuff on the left. Don't catch the stuff on the right. It'll proceed in a moment.
Pika,
one last one here. If we could have one more volunteer. We thought we'd recreate something from, in the yellow shirt, from Wednesday. What is your name?
Mary.
Mary. Come on up, Mary. And recall on Wednesday we introduced the notion of binary and binary bulbs. This is actually now an implementation of that same interface that we had on the iPad with the light bulbs, but here digitally rendered. And you know, rather than do a stress ball, nice to meet you, David. We brought some Hue light bulbs from Cambridge. If you can, clicking on those light bulbs to turn them on and off, come up with the binary representation of, say, 256. And you'll see in the middle the current tally. Yep, so that one's on. So the leftmost bit is on.
Yeah. Wait, isn't it 128 plus 128, 256?
Well, so we have just, oh, so this is the 128th column. So yeah, we're up to 128. We got to get to 256. And you can tinker on and off, no big deal. Or you can hit that 128 more times if you want. All right, good. 224. 8, yeah, getting closer. Closer. Oh. What's the problem then? So what's the issue? Well, so what do we need to solve this problem? So we need another bit. So, and this is perfectly reasonable in reality, right? If you want to count from the number 1 to 2 to 3 to 4 to 5, 6, 7, 8, 9, to actually roll over to 10, you're going to need an additional bit. So let's actually rewind here and come up with, that was obviously meant to be a setup. You can't do 256 with just 8 bulbs. So how about simply the number 50? The number 50. Excellent. A big round of applause for Mary and hers as well. Thank you. All right. So this topic, intentional as that was, will actually recur. The largest value that you can represent with 8 bits, or 1 byte, is indeed 256, but not if you start counting from 0, as we seem to keep doing by having all of those bits off. But now let's dive into the underlying implementation of this environment and tease apart some of these ideas. So in a moment, we're about to see a few different programming fundamentals, the first of which we'll call statements, sort of verbs, if you will, actions, things that should be done. And in a moment, you'll see blocks that look like this. Say hello world, for instance, or wait 1 second, or play sound meow. And indeed, the environment in which we're going to be doing this is called Scratch. And if I pull up Scratch without preloading any actual code, let's take a quick look at this user interface, so to speak, the controls with which we interact. On the top left here of the screen, below the menus, we have the stage, so to speak. So Scratch is what we'll call a sprite. It's a character, and he can be controlled by writing programs against him, and he'll be able to move up and down and left and right in this environment, not just by moving the mouse, but programmatically. I can tell him walk right, walk left, up, down, or the like, and I can introduce other sprites or characters as well. Indeed, on the bottom here is where you'll see your list of sprites. At the moment, I just have 1, but I can create more, and they'll appear exactly down there. So if you rewind for a moment, like Oscar time, for instance, Oscar on the left, the trash can, was a sprite. And the thing in the middle, the recycling bin, was another sprite. And the compost bin was another sprite. And every piece of garbage or recyclables that was falling from the sky is also a sprite, each of which was programmed individually. How do you program? Well, over here on the right-hand side is the scripts area. And this is where we can drag and drop puzzle pieces. In a week, it's going to be where we equivalently write code with more of a keyboard. But for today, it'll be dragging and dropping puzzle pieces, the palettes for which can all be found here right in the middle. Indeed, in the middle here, there's a whole bunch of categories of puzzle pieces or blocks. One's related to motion, looks, sound, a pen going up and down, data, events, control. I'm not quite sure yet what all of these mean, but you'll see that they've been nicely categorized. And to write a program in Scratch, let's do exactly that. I'm going to start off under events and drag this one here, when green flag clicked. Now, why that one? Well, recall when our volunteers came up, the first thing they did was click that green flag in the top right-hand corner, and that just means start the program. So when that event happens, what do I want to do? Well, I'm going to go under looks, and I'm going to do like say hello, and I'm going to change this and say something like hello Yale. And now I'm going to zoom out, click the green flag, and voila, I've written a program. It's not all that exciting just yet, but this is exactly where each of those authors started, both with Pikachu and the binary bulbs and Oscar time and so many more examples. You start super simple, and then you start to layer and add on features and functionality. So what are these layers going to consist of? Well, beyond statements, we'll also have things that are a little more fancily called Boolean expressions, after someone named Boole. And a Boolean expression is simply an expression that's either true or false, yes or no, 1 or 0, any polar opposites like that. It's either true or not. But we're also going to see ones that might look like this. So for instance, is the mouse down? They're sort of questions, if you will. The mouse is either down, true, or it's not, false, 1 or 0, if you will. It tends to be the mapping. True is 1, false is 0. Well, what about less than this? Or so is this less than this? That's a question of sorts. And if you put two numbers in there, either x is going to be less than y, or equal to y, or greater than y. But this block, we'll see, is just going to answer the question, is this less than that? We might also see something like this, touching mouse pointer. So in Scratch, you can ask the question, is the sprite touching the mouse pointer? In other words, is the cursor hovering over the cat or the equivalent? We'll see anding things together. You can ask two questions and make sure that both of them give you yes or true answers before making a decision to do something. But then how do you make decisions? Well, we have these conditions, and we saw this in our example of the phone book, looking to the left or right for Mike Smith. And in a condition, you do something potentially if a Boolean expression is true. And indeed, notice the shapes now. There's this placeholder right now on the overhead where we can fit, if I rewind one slide, that shape. It's not quite the same size, and indeed you'll see that Scratch resizes things dynamically to fit puzzle pieces, but the shape is what's important. This thing looks like that, and indeed it's roughly the same shape that should fit in there. And if we want to do something this way or that way, if or else, we have this puzzle piece in Scratch as well. Now suppose you wanted to do if, else if, or else. In other words, a three-way fork in the road. Well, what can you do just by glancing at this? I can take this puzzle piece, and it doesn't seem to fit, but again, Scratch is going to resize nicely for us. I can start to layer these things together. So now I have a three-way fork. If this is true, do this. Else, if this other thing is true, go this way. Else, go this other way. And in the Muppet movie, the fork in the road, so to speak, between Yale or Stanford was exactly that. Just two conditions, either go this way, else go that way. Well, loops also exist in programming, and we've used these already in class and in pseudocode, and surely in those Scratch programs forever. Scratch has this puzzle piece that will just let you do something forever. And sometimes you want to do something forever. It's not necessarily a bug. It's because you want a clock to keep going, or a game to keep playing. Or you can specify a finite number of steps, as with this repeat block here, which will repeat something 10 times. We can set variables, we'll soon see. And a variable, similar in spirit to algebra, like x or y or z, it's something symbolic that can store some value, some piece of information that you might want to remember for later. Best example of this might be a game where you have like a score, like in Pikachu, how many pieces of cake and whatnot did you catch? Well, that might be a variable called score that starts at 0, and then every time we caught a piece of cake or candy or the like, it gets incremented. It gets added to one at a time. And so a variable stores a piece of information like that. Then there's arrays, and we'll come back to these in a week or two time, but an array is kind of like an inventory or a satchel inside of which you can put virtual things. It allows you to store in more than one piece of information, and that might be useful if in a game you're sort of walking around picking things up, and maybe you want to keep all of those pieces of cake around and not just eat them one after another. And then there's a fancier construct we'll come to called functions or procedures. And though we're going fast here, we'll see that these are a very natural solution to problems that we're going to encounter as our programs start getting bigger. We'll start to notice patterns in the code that we're writing, the puzzle pieces we're dragging and dropping. And as soon as you notice yourself doing something again and again, or worse yet, copying and pasting programming code that you've written, that's probably an opportunity to factor out whatever you keep copying and pasting and putting it in something called a function. But more on those in much more detail before long. And then there's even fancier features. For those of you more comfortable or taking APCS or equivalent, Scratch actually supports things like threads and events and more, so realize that it has a fairly high ceiling, even though it's also very broadly accessible to folks who have never programmed before. So indeed, let's take a look at a simple program or two. We already looked at how we might say hello with Scratch. Let me go ahead and open up a little more interesting program that I wrote in advance, and this one's called Pet the Cat. All of these programs will be available on CS50's website, and indeed already there, so you can download them and play with them. And with problem set 0, which is also on the course's website, you're encouraged to walk through these. And moreover, we have a number of walkthrough videos online in which I and CS50's team truly walk through each of these examples at a much slower pace, a very fast-forwardable or rewindable pace, so that you can walk through these at your leisure as well. So here's Scratch on the left. Here's a program at the right that I've already pre-made. So let me zoom in on this. And could someone in English, knowing what you know just from now as to how Scratch works, sort of say in an English phrase or sentence, what does this program apparently do? Yeah, an orange shirt. Yeah, if your cursor is on Scratch, the cat, play a meowing sound. But notice how we express that. There's apparently a loop there, forever, and then there's a condition, the if expression, and collectively, what do those mean? It means this program's just always running, and it's just always waiting and watching and listening for me to move my mouse over the cat, because each time I do that, as you propose, it's going to do this. Let me start the program. Nothing seems to be happening, but notice how it's highlighted now in a yellow line. That just means it's running, and because there's a forever loop, it's still running. So let me move my cursor over Scratch. And if I move it off, now it stops, but the program's still running, and so adorable. All right, so let's open a slightly more advanced example called Don't Pet the Cat. And now let's see what happens here. Meowing, so it's a little different, sort of on autopilot, if you will. Don't pet the cat. I wonder why. Okay. So how did this work? Well, you can kind of reason through it intuitively, perhaps, but let's look at the actual code. So again, when the green flag is clicked, do this forever. What do you want to do forever? Well, if touching mouse pointer, then play a sound that's apparently called Lion 5 that's inside of this project, else play sound meow, and then wait 2 seconds so that it's not meowing incessantly. In fact, you can very quickly start to annoy yourself and your roommates. Let's remove this block. And notice what's nice about Scratch. Things just kind of drag and drop and interlock. So again, it grows to fill what you want. But if I remove this and then hit play, what's happening? It's kind of tripping over itself because it's literally doing what I'm saying. It's saying forever, play this sound, but I'm not giving it a chance to finish. And so that would be a bug, and that's why we had this thing in here now. So let's actually start from scratch, sort of pun slightly intended, in which we now have the cat move. So I'm going to do this on the fly. I'm going to zoom in here just to get me started on events. And green flag clicked, and there's other ways to start the script, so we're going to keep it simple here. And now I'm going to go ahead and go into control. And again, if you forget where these things are, just click around and eventually you find them again. So I want to forever do what? I want to use the motion block that I know exists, move 10 steps. All right, so let's see what happens here if I play this game. Okay, thankfully he doesn't go too far. I can still kind of grab him by the tail and pull him back, but the program's still running, so he's kind of fighting me. But it'd be kind of nice if I conditionally fix this in code, because this is not, actually this is really not a fun game for anyone of any age. Okay, so let's try to fix this by having some kind of condition. So I'm going to go under control, and then if. I like this idea. So after moving 10 steps, if, let me sense where I am. I'm going to go under sensing, and then it looks like I can go here. Notice the shape matches. Size doesn't, but it's going to grow to fill, and now this is a little menu, and now mouse pointer. I don't want the mouse, I want the edge. So Scratch is smart enough to know when a sprite is touching the edge, what do I want him to actually do? Well, let me go ahead and change motion. You know what? I'm going to have him turn around. All right, so at 15 degrees isn't really going to help me. I want him to turn around and go the other way. So let's see what happens here if I hit play now. Okay, kind of stupid looking, but it's doing exactly what I said, and it's rotating the whole sprite. Now, it turns out I can fix this, and I didn't know how to fix this at first. I kind of had to futz around and see the best way to do this, but if I go to, let's see, motion, I found this. Actually, set rotation style, left, right, or don't rotate, or all around, and it turns out that's what I want. And I'm going to put this not in my loop, because I don't need to set the rotation style multiple times. I'm going to put it at the very top of this program so that it gets set once and then remembers. And now I'm going to try this again. Let me stop the program. And now that fixed that bug. All right, so I'm iteratively improving upon this. The program's getting a little more complex and bigger, but I'm taking baby steps, so to speak, and small bites out of the problem to get it better and better. But this, too, is kind of lame. You know what? Would someone with a really good, frightful voice like to come on up? Someone with a voice. Yeah, come on up. in the green shirt. So it turns out there's some other fun things, aesthetics and sounds alike. Here's the meow. I clicked on the sounds tab. There's the meow that comes with Scratch. But you know, we can actually record something of our own here. So let's do exactly that. Instead of using this cat sound, let's go ahead here. And what's your name?
Nick.
Nick, nice to meet you. It's David. So in a moment, I'm going to hit the record button. And if you can just yell into the laptop like, ouch, as though you just walked into the wall, that'll be much appreciated. All right. All right, 1, 2. Ouch! Awesome, and now we can do a little editing here. I'm going to get rid of the quiet part, and I think that's good. All right, thank you very much.
Yeah. Pleasure.
All right, I've just renamed it Ouch, but now I'm going to go back to my scripts, and notice there is indeed sound here, and I'm going to go ahead and play the sound Ouch, and I'm going to do that if it's touching the edge only, and then I'm going to have it turn around. So let's see what happens here. Let's go full screen.
Ouch! 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 Ouch!
Amazing.
Ouch! Ouch!
To realize that we're getting a little lucky. I'm going to have him move like 100 steps at a time, the effect of which now is going to be... So within reason. So an opportunity to refine that further if we really wanted to. So now let's introduce another concept. So let me go into one called counting sheep and use something called a variable. This is an adorable little sheep, and I've changed his costume, so to speak. So even though the default's a cat, you can upload, you can draw, you can do any number of characters on your sprites. Here's a program that's going to do what in English? Based again on just what you know now. What's this program do? Yeah, it's going to count one number at a time. So when we apparently have this set counter, I don't know what that is, but maybe it's a variable, right? It's just a container, X or Y, but the word counter is more descriptive than a mathematician's X or Y, so we tend to use English words for things. Forever just means keep doing this. Say counter. Now, where did this come from? Well, it turns out that counter is a variable, so it's just another puzzle piece I created in advance, and even though it happens not to be the same shape here, normally you would say something like hello here, you can also drag a variable so that that's what gets said. Then I wait for a second, I change the counter by 1, incrementing it by adding 1, so that the net effect is this adorable counting sheep, though he's counting himself. Now, it's very quickly going to get boring because he's going to do this truly forever, but that's exactly what the program's design prescribes. Let's now try another example that leverages a variable, this one called high, 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 that does get annoying quickly. Now, this one has 2 scripts, and so again, we've taken baby steps. We started with something super small, added to it, added to it. Now I want him to do something even more dynamic, so I want to kind of be listening for 2 different things at a time. So on the left, when green flag is clicked, I set a variable that I wrote in advance called muted, and I arbitrarily set it to 0. So Scratch doesn't have true and false, but it does have 0 and 1, so I can approximate that same idea. And then forever, if the space bar is pressed, then set the variable to 0. Or sorry, if the space is pressed, and if muted, the variable, is 0, then set muted to 1, else set muted to 0. This seems sort of like we're just doing and undoing work, but what's the effect? Every time I hit the space bar, what happens to my variable called muted logically? Sort of gets flipped. It changes from 0 to 1 or 1 to 0. So it took a few blocks to express that, but all I'm doing is toggling the state of this variable to 0 or 1 or 0 or 1 each time I hit the spacebar. Now over here, what's this doing? Forever, if muted is 0, so if muted is false, so if it's not muted, is the semantics there, play sound sea lion and think hi, hi, hi for 2 seconds, wait 2 seconds. So notice now these scripts are effectively going to run in parallel so that one can be listening for one action, the other can make a decision based on that action, and it can do this forever. So it's going to do this forever until, as I've just done, and now it's still running, but I've muted the game. And that's all this guy does now, too. Let's open another example here. Let me go into events. And now this, adorable too, but notice it has 2 sprites. So not just 2 scripts with 1 sprite, but 2 sprites. And if I click on the blue guy as I already have, I see he has one program up here that literally just says this. When I receive an event, say polo for 2 seconds. So if you've ever played in like a pool, the game Marco Polo, if the orange guy's script is any indication, Apparently, every time I hit the space bar, what's the orange guy going to do? He's going to say Marco, and then this is a new block. We've not seen this before, but broadcast an event. And I could call it event anything we want. We'll come back to this perhaps before long. But broadcasting an event is a way for one sprite to talk to another by essentially passing it a message. It's not a message you see. It's not something visual. It's sort of a computer message that the other guy is listening for, because indeed the blue guy, recall, doesn't have when green flag clicked. He instead has when I receive an event. When he gets handed this note in class, so to speak, he should say Polo. And so the net effect is that when I hit the green flag, nothing happens, but when I hit the space bar, he says Marco, he responds with Polo. But the only sprite I'm interacting with is the orange one. So this is a way of kind of passing messages between sprites and having them communicate with one another. Now let's look at one last one here called threads. Now notice this by playing it. So these are two sprites. The bird's kind of flying around. He's bouncing. There's no ouch, but same idea. But the cat seems pretty smart. What is the cat apparently doing? And, wait for it. What is the cat apparently doing? It's not just bouncing. He's following the bird. And so apparently there's a way with a combination of blocks here, and let's look at the cat real fast. Forever, if touching bird, then play the sound lion 4, whatever that is, we heard it once. Otherwise, point towards bird and move one step. Now, the fact that it's one step is what gives the bird a bit of an advantage initially, but if we instead make this 10, for instance, so that every iteration of the loop he's moving 10 steps at a time, so more space, let's see what happens then. Not all that much better. So now let's try to improve upon these a little iteratively and come back to that notion of a function, and indeed one of the fundamental takeaways of the class, design. Not just writing programs that work and that are correct, but are well designed. And design is much more subjective, and you'll get better at it over time, but let's take some baby steps towards starting with a program that works, absolutely, but it's not very good. It's not very well written. So here's a program that does this. Cough, cough, cough. What does the program look like? Looks correct to me. It's saying cough for a second, then it waits, then it says it again, then it waits, then it says it again, and then it waits, and then the program implicitly ends because there's no loop. But why is this a badly written program, even if you've never programmed before? Like, what rubs you the wrong way, perhaps, here? Yeah? Exactly. You're repeating yourself again and again, and literally, I copied and pasted 2 of those blocks again and again, and that's exactly the sort of sanity check that you should be making. Wait a minute, should I really be doing this? So what's the obvious solution, perhaps? Have some kind of loop. And I don't quite recall what the puzzle piece is, but if I look at the next iteration here, indeed, there's not just the forever loop, there's repeat some number of times, and so I've specified 3, and now notice how much tighter, how much more succinct this program is, and in a sense, how much more maintainable. If I want to change the word from cough to something else, like achoo, like he's sneezing, then I change it in one place and not 3. So this already feels like slightly better design. Let me instead open cough 2, our third example, and notice as a computer scientist, I start counting at 0 typically. Now this looks a little scarier at first, but the effect is the same, cough, cough, cough. But what seems to be fundamentally new in the top part of the program? I've removed the say, I've removed the wait, and what have I plugged in instead? A function, a cough block. I mean, frankly, I seem kind of an idiot if I didn't just start with the block that's apparently called cough, if that's all I want him to do. But that doesn't exist in Scratch. Rather, I went to one of the palette called more blocks here, and I dragged this big purple thing here that lets me define a function. It essentially lets me create my own puzzle piece that can be called anything I want, that can do anything I want, but it gives it a name. It gives me a new purple puzzle piece that now does whatever I tell it to do. So this purple piece here corresponds to this one here, and what does it do? It says cough for a second, and then it waits, and now I've sort of created my own custom puzzle piece so that it behaves exactly that same way. So I can keep doing this, and indeed there's going to be more and more opportunities for modularization and for layering complexity on top of one another, but this basic idea, indeed in problem set 0, what you're going to be challenged to do is to download Scratch and or use it on the web and just have fun with it. We'll give you a set of requirements, having a sound and some number of puzzle pieces, but you'll do exactly this, and you'll realize that you're going to want to take some baby steps initially until your program gets more and more complex, but considering, is this the best way I could do this? Can I avoid this instinct perhaps to copy and paste? But before problem set 0 and before we adjourn, I thought we'd take up one more volunteer if we could for a final program that's perhaps the most fitting at all given today's venue. Come on down. Yeah. Yes. What's your name? Uh-oh. Okay, that's okay. Both come down. And I will deal with this somehow within the next 10 seconds. So come on down, come on down. Let me come on up here. Come on. All right. All right. Let's see here. So notice real fast here, if you'd like to come on up, we'll do 2 rounds of this. And what's your name?
Sabrina.
Sabrina and?
Yingji.
Yingji. Nice to meet you both. David. So our final example here is called Ivy's Hardest Game. And why don't we have you do level 1 and you do level 2, and we'll see how far beyond that we actually go. Written by a student last year, remixed by me so that this would go over well in New Haven. And I give you a game that's going to involve moving the arrows up and down and getting Yale to the finish line. Here we go.
You can't touch this. You can't touch this. You can't touch this. You can't touch this. My music hits me so hard, makes me say, oh my Lord, thank you for blessing me with a mind to rhyme and do like it feels good. When you know you're down, a super dope homeboy from the Oak Town, and I'm known as such, and this is beat you can't touch it. I told you, homeboy, you can't touch this. Yeah, that's how we living, and you know you can't touch this. Look at my eyes, man, you can't touch this. Yo, let me bust the funky lyrics. Touch this. Fresh new kicks and bands, you got it like that. Now you know you wanna dance, so move out of your seat and get a fire girl and catch this beat while it's rolling. Hold on, pump a little bit and let them know what's going on like that. Like that. Pull a little bit, just fall on back, let them know that you're too much. And this is a beat they can't touch. Yo, I told you, you can't touch this. Why you standing there, man? You can't touch this. Yo, sound the bell, school is in, sucker. You can't touch this. Give me a song, a rhythm, make them fat. They know, they talk about the hill, they talk about a show that's hyped and tight. Singles are sweating so fast, I'm a whiteboard tape. To learn what's gonna get in the 90s to burn the charts. Legit, either work hard or you might as well quit. That's the word, because you know you can't touch this. You can't touch this. Break it down. Stop. Hammer time. Go with the flow. It is said if you can't prove the list, you probably ought to dance away. Your hands in the air. This is it. For a winner, dance to this, and you're gonna get there. The move, slide your rump. Just for a minute, let's all do the bump. Yeah, you can't touch this. Look, man, you can't touch this. You better get hype, boy, because you know you can't touch this. Ring the bell, school's back in. Break it down.
About that.
Time.
That's it for TN50. Thanks so much for joining us. See you outside.
Hey, David.
Hey David, how's it going?
Good job today.
So have you thought about what you're going to do for the outros?
I got nothing.
What if this is the outro?
Like unpacking carts?
Uh-huh. You know, it's about nothing.
So like no story, no conflict, no resolution. I don't understand. What's it about then?
Nothing.
So we have outros about nothing, and we have no actors? Who's gonna be in this?
No. I mean, I'll be in it.
You'll be in it.
Yeah, people are always telling me I'm a character.
Well, I mean that's true, but who else is gonna be in it? It can't just be you.
You will be in it. Davin, Dan, Colton, Zamila, Elise, Doug, David, everybody.
So it's about nothing, and everybody's in it.
Absolutely nothing.
This is ridiculous.
So the final number of people in a room that has 497 seats is, all of which are filled, is 390. Okay, so this is great. We will soon discuss the notion of a bug in a computer program, but we'll come back to that before long. But in theory, what might have happened just now? So even though there were 3 big steps to this algorithm, each of those was just kind of one big operation, and there was this cyclicity to it in that if you were still standing, you kept going from step 3 to 2, step 3 to 2, step 3 to 2, but what kept happening on each iteration, each cycle of this loop? What was happening elsewhere in the room? Not only the same thing, but what was happening to half of you? Sitting down. And so therein lies this insight, much like the phone book example, in that if half of you are sitting down each time, the problem is starting with maybe 400 people, then to 200 people, then 100 people, then 50 people, and so forth, until we whittle it down, in theory, to just one person thinking of the total value of everyone. Now, in reality, some social dynamics and some arithmetic errors might contribute to that ultimate bug, but in theory, while I was still counting away, taking several dozen steps or hundreds of steps to count yourselves, to count a room full of 500 or so people should have taken far fewer steps, because you can only divide 500 in half so many times. And so just like with the phone book example the other day, did we have something logarithmic, so to speak, whereby if we were all operating in unison and ignoring the addition errors, would we have achieved exactly that kind of running time? Now, to be fair, kind of cheated in that I leveraged another resource, right? Whereas it's just one of me, I leveraged hundreds of you, but that might be said to be an example of parallel processing, a state of art very much in vogue, where computers these days have multiple CPUs, or more technically, multiple cores, and can truly do multiple things at once, much like you all were doing there in parallel. But recall that what we also did on Wednesday was try to capture this intuition and formalize it in code, something like pseudocode. And in fact, and I hope you'll forgive, it's like 80 degrees in here, so I'm going to take this off for just a little bit. What I thought we'd do is transition now to an application whereby we again engage the audience, but write a program in English-like syntax with which to solve this problem here.
It's peanut butter jelly time. Peanut butter jelly time. Peanut butter jelly time. Where you at? Where you at? Where you at? Where you at? There you go. There you go. There you go. There you go. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Do the peanut butter jelly. Peanut butter jelly. Peanut butter jelly with a baseball bat.
In that video, but it is a little addictive, if not a bit annoying. But to do this, I thought what we'd do is try to write a program together for which we need 3 volunteers. Have to be comfortable on camera and the internet. Sam, come on up. Okay, purple shirt right here. Come on up, and from over here, let me go a little farther back. Crimson and blue shirts. Come on up. Perfect. And come on up. Come on up. Come on up. All right, and what's your name? Erica. David, nice to meet you. If you'd like to take this seat here, this is Sam. And what's your name? Antonio. Antonio, nice to meet you. Erica and Sam, if you'd like to have a seat here. What we've come prepared with, as these guys are discovering, is the ingredients with which to make a peanut butter and jelly sandwich. Now, this might be something that you take very much for granted, but we've given each of our 3 volunteers here, or 2 volunteers and Sam here, a loaf of bread each, a plate, a knife, a jar of jelly or jam, and a jar of peanut butter. And the goal at hand now is going to be for these 3 to make a peanut butter and jelly sandwich. But what we're going to do is expect the audience, since all of you surely know how to do this so well in reality, are going to provide us with the step-by-step instructions, the pseudocode, if you will. So I'll play the role of scribe here, and I've got a little to-do list. And so as each of you one at a time calls out a potential instruction, I'll write it down, repeat it as needed, and then you guys are going to make a peanut butter and jelly sandwich only by doing what you are told. So think of yourselves as computers. You can only do what you're told. No assumptions, no questions. You just need to do it. So who would like to hazard the first instruction for making a PBJ sandwich? On the balcony there.
Open the bag of bread.
Open the bag of bread, if you will. All right, so let's iterate and get a little more precise. Good way to begin, though. Step 2, someone else. Oh, now no one wants to volunteer. Step 2, in front.
Open the inner bag of bread as well.
Open the inner bag of bread as well. Great, we're learning.
If you come to a fork in the road.
Yes, sir. Turn left at the fork in the road. Turn left.
I don't believe that. Moving right along, we found a life on the highway.
And your way is my way.
So trust my navigation.
Movie stars with flashing cars and lights with the top down.
We're storming the big hill.
Yeah, storm is right. Should it be snowing?
No, I don't think so.
Moving right along.
Footloose and fancy free.
You're ready for the big time.
Is it ready for me?
Moving right along. Moving right along. Moving right along. Moving right along.
Maybe you better pull over.
Yes, sir.
This is CS50, and this is the end of week 0, but the start of a beautiful friendship. We are so excited to be here at Yale University for the very first time with our friends Skaz and Jason and Andy, all 40 of CS50's TFs and CAs here at Yale, and all of you. And in fact, it's probably time to... Even though most of the lectures will indeed be in Cambridge this year, the reality is that by design and very much deliberately in CS50, I do think we're nearing the point, technologically and pedagogically, where it can be a superior educational experience to engage with some of the course's material online. Indeed, the reality, and I believe this philosophically, is that lectures are not a particularly effective means for delivering fairly complex information, certainly over hour-plus long spans of time. And indeed, every few minutes, I remember myself in college, you zone out for a moment, you miss some complex topic, and you're gone pretty much for the next 45 minutes. And the reality is that whether you're here in New Haven or Cambridge or beyond, the simplicity of having the ability to pause and fast forward, rewind, hyperlink to related resources, search full text transcripts and the like is an opportunity that I dare say for our online students well beyond New Haven offers them an opportunity to really grasp the conceptual material that we introduce in lectures all the better. But ultimately in CS50 is the student's experience is characterized so much more by the course's problem sets or weekly programming projects, the course's sections led by the teaching fellows, the nightly office hours led by the course assistants and the teaching fellows, and indeed such events as CS50 Puzzle Day, CS50's Hackathon, the CS50 Fair, weekly lunches, and so much more. And so whether you're here in New Haven or tuning in from afar today in Cambridge, and we'll see you again soon, the reality is this is one and the same class, and we are so excited to be here all together today. And so at the end of the semester, whether here or afar, well, hopefully you wear proudly, happily, and perhaps with a bit of relief, the shirt that bears witness to you having taken CS50. So where did we leave off on Wednesday? We took a look at computational thinking, and that's to what we distilled computer science into, at least for now. But we distilled it further into at least 3 component elements. Inputs, so what is the problem we're trying to solve? Outputs, what is the answer we're hoping to get? And the representation thereof. And we won't dwell here on after on binary and even ASCII and the like so much, but rather take for granted that we can represent this information, because the far more interesting parts of those problems are not just the inputs and outputs, but the algorithms that go into solving those problems. And you might recall from the other day that we took a fairly traditional concept of, all right, a little more precise. Let's get this working. Yes, in green shirt.
Gently remove 2 slices.
Slices of bread. Gently remove 2 slices of bread. That's good. Step 4, someone else. Over here, yes.
Bread on plate.
Place bread on plate. Step 5. Step 5, yeah.
Lightly place hand on top of peanut butter.
On top of, oh, hand. Place hand on top of peanut butter. Is that what I heard?
Yeah, and unscrew.
And say it again.
Unscrew and put the lid next to it.
And put the lid next to the peanut butter. Lightly place hand on top of peanut butter and unscrew and put the lid next to the peanut butter. Okay, step 6. Step 6. Someone else, yeah. And say it again. And repeat step 5 again. Which is going to create a bit of a problem now if we're doing this step by step. So now we go back to step 5. Lightly place hand on top of peanut butter and unscrew and put lid next to the peanut butter. Then grasp the peanut butter and repeat step 5 again. All right, so we'll override that infinite loop, if you will. Step 7, someone else. Yeah, and back.
Grasp lower half of the peanut butter jar with one hand and top with other. Turn it opposing direction.
Okay, wait. Okay, and on top of other. On the other hand, on the other top. Do you want to just come up here? Okay. Anyway, how do I finish the instruction? What's the rest of the instruction? Ignoring that part. Okay, so let's start over. Step 7. Grasp with opposing hands. This is good. This is actually good. And plastic jar. And twist. For 2 seconds. Okay, just open the peanut butter jar. Okay. I hope you'll forgive. Okay, so let's assume we got there. Open the peanut butter jar. Yeah, excellent. All right. All right, step 8. Let's go. Step 8. Yes, in back. Insert. Good. Step 9. Yes. If out of the peanut butter jar and what? And put knife back into peanut butter. Good job. Okay. Okay, step 10. Step 10. Put the knife out.
And then remove the seal.
And then remove the seal. Nice.
Off the peanut butter.
Off the peanut butter. All right, step 11. Yeah.
Gray computer follow blue or red?
Wait, say again?
Gray computer should follow blue or red.
Oh, gray computer. Okay, gray computer follow blue or red computer. All right, good. Looking someone up in a fairly large phone book, or more generally, digitally these days, just a very large data set, a really big contacts list with lots of names alphabetically sorted, and we realized that while I could approach this problem simply by using a linear approach, page by page, or even twos at a time, we realized that the more intuitive algorithm, just kind of dividing and conquering the problem again and again and again, having it with each time, gave us this green result. And it's so much flatter because it suggests that even as this problem gets bigger and bigger, as is the case these days with data sets in reality, Facebook and Google search results and the like, does our algorithm perform just as effectively with those bigger bytes as it did even with the smaller bytes. Now, it begs the question, what can we actually solve similarly with this kind of intuition, this sort of division and conquering? Well, we could do something like this today here. We could take attendance, so maybe like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Not going to be all that efficient. So wait, grade school, 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. But could we do a little better? I'm pretty sure I can't do this by myself. So if you'll humor us for just a moment, we brought with us an algorithm that's just got 3 steps, but it does require, if you don't mind, that all of us stand up, if you would. So, with all of us now standing, step 1 of this algorithm is the following. Stand up and assign yourself the number 1. So at this point in time, literally everyone in this room, hopefully, is thinking to themselves, however awkwardly, the number 1. Now, step 2 of this algorithm is going to involve the following. Step 2, pair off with someone standing, add your numbers together, and adopt the sum as your new number. All right, quick sanity check. What number is everyone thinking of now? All right, so 2, except maybe for one awkward, lonesome person if we have an odd number of people in the room. All right, so one person might still be the number 1, that's fine. But step 3 here, one of you should sit down, the other should go back to step 2. And repeat if you would. So if still standing, you should be among those going back to step 2. Keep going. All right, few people still standing. So if still standing, pair off with someone. All right, whittling down. Few people still standing. I'll help if need be. Remember, the key takeaway here is how much faster this is than me counting. So let's see. I can help out. So what number are you still thinking of?
I got 44.
44. So you go ahead and sit down. What number are you thinking of?
74.
74. All right, go ahead and sit down. Who else is still standing? 86. And is anyone else still standing? What number? Okay, wait, I heard 67. And then in top? 32. Anyone else still standing and thinking of a number? Oh, hi, sorry. Be right back. 42. Anyone else? Okay. 47. Is anyone else still standing who hasn't been counted? All right. Bring us home. Couple more steps. What's next? Step 12. Step 12. Yeah.
Put one of the slices of bread, like gently, on.
One of your hands. And then step 13. Yeah.
Use knife to gently spread peanut butter onto slice of bread.
On slice of bread. Good. Pretty good. Step 14. 14, yeah.
Undo step 13.
Undo step 13. Let's move on to the jelly. Come here. This is a 100-step program. We're on step 15. Yeah.
Repeat step 7 through 13 using the jelly.
7 through 13 using the jelly, because those went so well. Okay. Repeat steps 7 through 13 using the jelly. So grasp the lower half of the jelly jar with one hand on top, on the other hand of the other top, ignoring that part. Grasp with opposing hands the lid and the plastic jar at the bottom and twist for 2 seconds. Then open the jelly jar. And lastly, let's try to give us something edible. Step 16. Last step. All right. So why don't we leave it there? Thank you so much to our 3 volunteers. If you'd like, we have a CS50 stress ball for you.
Oh,
It's going.
Do I get one too?
Yeah, it was going to be a sandwich, but okay. All right. So what was the point beyond having a bit of fun with the algorithms? But the reality is that even when you're programming a computer, you need to be super precise, right? As complex or intimidating as your own computer might very well be to you, at least when something goes wrong, the reality is it's a pretty dumb device that was invented by us humans and can only do a subset of what we do, sometimes certainly faster, but it doesn't know how to make assumptions. It doesn't know how to be on the same wavelength as you. It will only do precisely what you tell it. And you'll be struck, perhaps, as we start writing actual code with the first problem sets and beyond, just how easy it is to make an assumption as a human and not anticipate, oh, I need to handle that case or that corner case, so to speak, that might very well arise if, for instance, Sam had the only squeezable jar of jelly, whereas everyone else had some glass jars as well. So before we turn our attention to some actual code, allow me to introduce the course's heads here at Yale, our friends Skaz and Andy and Jason, to come up and say hello.
Jason somewhere. We've lost Jason temporarily. Okay. Hi again, everyone. My name is Skaz. I've been teaching at Yale since 2001. And when I'm not teaching, my research is in robotics and artificial intelligence. And the announcement that I have today is that starting in a couple of weeks, we're going to be bringing some supplementary material to CS50 to talk about intelligent software. We're going to talk about how places like Netflix and Hulu can recommend movies that you might want to watch. Or we'll talk about how driverless cars actually work. And we'll be able to ground these things in the concepts that you're learning in this class today. Because all of these things are built upon the same foundation. And that's what this series will explore. So I'm really looking forward to seeing more of you all, and you're going to get to see more from all of us very soon. Let me then introduce Jason.
Hi, everyone. My name is Jason. I, unfortunately, went to Harvard as an undergrad. That's going to get cut out of the actual stream. And now I'm here as a lecturer in the computer science department, and I'm helping run the course with Skaz, David, and Andy.
All right, hi guys. So my name is Andy. I am actually the only Yale student on this stage right now. I'm in Berkeley College, originally from Solon, Ohio. There we go. And I was one of those kids where when I came to Yale, I really thought that like I would never have to look at a number ever again. And then I realized that you needed both science and QR credits to graduate. And so my freshman spring, I took a class, a intro CS class here at Yale. I was like, this is like actually pretty cool. And why